When talking about navigation, most people envision this: sitting in a car and driving to your destination, guided by a smart device. It tells you where you are and where you need to go. All you have to do is operate the car, and sooner or later you will reach your goal. You may ask, why are we talking about driving a car? Well, navigating on Earth is similar to navigating in space, at least when we look at definitions. So let's divide the commonly used term navigation and compare it to space travel. We have guidance, navigation, and control. Let's start with guidance. We can put it in simple terms and define it as: what do I need to do to my vehicle to reach my goal? In a car it might be turn left. In space it might be accelerate in this direction at a specific time. The next point is navigation. Where am I? In a car it might be GPS coordinates or maybe just a street sign. In space it's where am I, how fast am I, and in which direction am I moving. Finally, we got control. How do I need to operate my vehicle to fulfill the guidance? In a car it might be accelerate, brake, or move the steering wheel. In space it's how long and in which direction do I have to burn my engines. On Earth, guidance and navigation are pretty simple, at least if you know where you are. And vehicles usually behave in an expected manner. We turn our steering wheel to the left and our car moves to the left. We hit gas and we go faster. In space it's a little different. To understand why guidance, navigation and control are so important, we need to take a look at some simple orbital mechanics and understand the concepts. One might ask, why not just point your rocket to the moon and fire your engines? And thanks to modern computers and video games, we can take a look at what would happen. Here we are orbiting a planet in a circular orbit. And let's point our rocket to the moon and light the candle. We can immediately see how our orbit is changing. In this case, badly for our astronauts, since we will be falling straight into an ocean. Let's roll back and see what happened. Here we are a few seconds before our burn. Notice the nav ball. Our orientation in space is almost retrograde, meaning that we are flying in a reversed position. Therefore, firing our engines would just decrease our orbital speed and drop our periaps into the planet. Let's take a look at this in more detail. Once again we are orbiting a planet. Imagine we are going counterclockwise, meaning that our rocket is flying nose first in flying direction, also known as prograde. Here we also got our periaps and apoaps labeled in the picture. The apoaps describes the highest point in an orbit, while the periaps describes the lowest point. If we burn our engine in this direction, we increase our orbital speed. By increasing our speed, we are not changing the point we are currently at. We are increasing our orbit on the opposite side, meaning that in this case we are raising our apoaps. Now let's turn our rocket by 180 degrees, pointing it engine first in his flying path, also known as retrograde. By burning our engines now, we decrease our orbital speed and therefore lower the orbit on the opposite side. Now you may have concluded why we couldn't point our rocket straight at the moon in our example. The moon was in such a position that burning towards it would lower our orbit on the opposite side because we were pointing retrograde, leading to a re-entry in the planet's atmosphere. So how does that help us get to the moon? On this picture we can see the rocket's path schematically. Notice that we start the translunar injection on the opposite side of the world compared to the planned encounter with the moon. Remember that increasing our speed in an orbit influences our apoap side on the other side. So in this case, we raise our apoaps on the other side so high that we cross the moon's orbit. We also have to consider when we initiate the TLI. Notice that the moon is not at its destined point when we start our engines. The moon, as everything else in space, is in constant motion. So it's not enough to just raise our orbit, we also have to time it precisely to encounter the moon. Another point is that small errors at the TLI will add up to big errors once we are on the other side of the orbit. So it's necessary to do some mid-course correction maneuvers along the translunar coast to correct small errors from the TLI. And that's why guidance, navigation and control are one of the most crucial parts in space travel. Now that we understand why the GNC is so important, we can finally take a look at how the Apollo missions achieved it. Here we got an overview of the command module system. Let's start with probably the most crucial part of the navigation system, the inertial measurement unit. Its job was to provide an inertial reference frame and measure attitude and acceleration changes of the spacecraft. The heart of the system was the stable member, also referred to as the stable table. It consisted of a 6-inch beryllium cube with 3 gyroscopes and 3 accelerometers, making it possible to measure attitude changes in yaw, pitch and roll, as well as translation within the inertial reference frame. Now let's take a look at that in more detail. Here we got a functional diagram of the IMU. In the middle we can see our stable table, with the 3 gimbal axes around it. The outer gimbal was mounted fixed with the spacecraft. By turning the spacecraft, the gyros would detect a change in attitude and feed the data back in a resolver, which would operate the torque motors. This servo feedback loop would keep the stable member in a fixed orientation within the inertial reference frame. The orientation and specific force of the geometrical reference member was then measured by the specific force receiver, and the data was fed into the Apollo guidance computer for further processing. Here we can see the scientists of the MIT Instrumentation Laboratory, which was later named Draper Laboratories, testing the IMU. Since the IMU was a mechanical device, it was usually shut off during long coast flights. It was only turned on and recalibrated when a navigation measurement was necessary or when velocity-altering engine burns were planned. The IMU in itself was not perfect. The system drifted around 1 millirad per hour, which made periodical realignment necessary. The next crucial part for the navigation system was the optical system. It consisted of a precision 2 line-of-sight sextant and a single line-of-sight scanning telescope. The optical system provides the onboard measurement capability for orbital and mid-course navigation, as well as system alignment capabilities for the IMU. Here we see a functional schematic of the space sextant and the side scanning telescope. The sextant, as seen on the left, is essentially a 2 line-of-sight instrument similar to a sextant a sailor would use. It provides a 28 times magnification for manual use, as well as special sensors for automatic use. It is seen on the figure that one of the line of sights responsible for the landmark side of the navigation angle is undeflected and therefore fixed with the command module. To aim this line of sight, the whole spacecraft must be turned by means of orientation commands to the attitude control system. The second line of sight, identified with the star side of the navigation angle, can be pointed in space through the use of 2 servo motors, as shown in the schematic. One axis, called the shaft axis, is parallel to the landmark line and changes the plane in which the navigation angle is measured by rotating the head of the instrument as a whole. The second axis, the trunnion axis, sets the navigational angle by tilting the trunnion axis mirror. A precision angle data transducer on this mirror provides a direct measure of the navigation angle for the navigation routine of the computer. An angle transducer on the shaft axis completes the data needed by the computer when the instrument is used for inertial system alignment. Because the 28 power magnification of the visual section of the sextant results in a less than 2 degree diameter field of view, the second instrument, the scanning telescope, provides a wide field acquisition capability for the sextant to find and acquire objects in the sky. The scanning telescope, as seen on the right, has its shaft and trunnion pointing in a single line of sight. The shaft angle follows the sextant shaft angle by servo action when the system is powered on. The trunnion can be selected by the astronaut to follow the sextant's trunnion and therefore look at the star line, be driven to 0 degrees and therefore look at the landmark line of sight, or be driven to a fixed angle of 25 degrees to simultaneously acquire both landmark line and star line of sight. Here we can see how the navigation system was mounted. It was crucial that the IMU and the optical system were mounted in the same subsystem to keep the error of the IMU angles and the sextant angles as small as possible. On the bottom we can see the Apollo guidance computer. The inertial measurement unit is inside the navigational base, and on top we can see the optical unit. Here we see an image of Jim Lowell operating the guidance and navigation system during the Apollo 8 flight. Now we can take a look at how the optical system was used to align the IMU, determine the position during translunar or trans-Earth coast, and while orbiting the Moon or the Earth. Let's start with the IMU alignment. Every Apollo mission had a so-called star chart on board. It's a map of stars which coordinates are known within the inertial reference frame. Those coordinates were hardwired into the memory of the Apollo guidance computer. By carefully measuring the angle between the spacecraft and multiple known stars, the Apollo guidance computer was able to calculate the current orientation in the inertial reference frame. This orientation was then used to drive the torque motors of the IMU to align its stable member. Now we can take a look at the orbital navigation. When the spacecraft is in orbit around the Earth or the Moon, the measurements are taken on predetermined landmarks for updating the velocity and position. Due to the high angular rate of the landmark with respect to the spacecraft, the wide-angle scanning telescope was used for tracking and taking optical measurements. The landmarks chosen as optical targets during the orbital navigation had to be close to the orbital ground path, so that the target image acquired near the horizon is tracking along the path which passes beneath the spacecraft. For this procedure, the IMU must be recently fine aligned to obtain maximum accuracy for orbital navigation measurements. The astronauts then had to choose a landmark and send a landmark code to the computer, similar to the star chart we saw previously. Then the optic shaft and trunnion angle had to be driven to the required angles. After that, the astronauts centered the landmark in the telescope and pressed the mark button to send the angles to the computer. About 3 equally spaced marks are taken on each target. The computer was then able to calculate the current position and the velocity of the spacecraft using the measured angles, the orientation given by the IMU, and the current time. And finally, we got the mid-course navigation. This was performed during translunar or trans-Earth coast to verify that the spacecraft was on track or if correctional burns had to be done. For this, the astronauts took an angle measurement between a known landmark and a known star with the sextant. If a landmark couldn't be seen due to cloud coverage, it was also possible to take the measurement at the Earth's or Moon's horizon. Upon initiating a mark command, the angle between the star, the landmark, and the time of the measurement are recorded. The recorded data defines a cone in space as seen in this picture. The apex of the cone lies at the landmark. The size of the cone is dependent on the measured angle, which is equal to 1/2 of the cone's angle. The cone axis is parallel to the star line of sight for any arbitrary point on the cone. The angle between the landmark and the star are the same. Therefore, one sighting defines the spacecraft's position somewhere on the surface of the cone. The point on the cone surface closest to the estimated position becomes the new improved estimate of position and velocity at the present time. The estimated position comes from the Apollo guidance computer. The expected velocity and position are already calculated before the translunar injection based on the inertial subsystem velocity measurements and the gravitational model. Solving the equation of motions, the projected position is obtained by extrapolation and an estimated trajectory is established. By doing the mid-course navigation measurement, the computer compares the actual measured position and velocity with the estimated one. The difference was then used to update the estimate internally. This concludes the navigation. We can now identify where we are in space and how fast we are moving thanks to the IMU, the optical system, and the Apollo guidance computer. The AGC was also used for guidance. As we discussed earlier, the Apollo guidance computer calculated the estimated position and velocity based on the measured values. This model was also used for guidance. By knowing where the next destination is, the AGC calculated the needed velocity change to match the desired trajectory. As we can see in this example of a mid-course correction, the desired trajectory goes along the dotted line. Our current trajectory follows v1. Since the velocity is a vectorial unit, we need to increase our velocity along v2 to get to the desired trajectory. The translunar injection worked on a similar basis. As we remember, to increase our APWAPS, we need to increase our speed. The AGC calculated the necessary speed and the position in orbit, compared it to the current position of our spacecraft, and was able to calculate the necessary change in velocity. So now we know where we are and where we need to go. The final step is control. For this, the command and service module was equipped with the so-called reaction control system and the service propulsion system. The reaction control system, or just RCS, consisted of thrusters that were installed around the spacecraft, providing the capability for attitude control, stabilization, and minor velocity corrections. The service propulsion system was the main engine of the command module and was used to bring the spacecraft in and out of lunar orbit and for mid-course correction. To see how the control was performed, we can take a look at the whole guidance, navigation and control system of the vehicle. Here we can see a schematic of the GNC. On the bottom we have the astronaut, working in the monitor and optional operator loop. This was the interface for the astronaut to input commands, monitor the spacecraft, or manually perform maneuvers. Then we got the guidance and navigation system, performing the tasks that we discussed previously. Next we have the control and information system, being part of the stabilization loop together with the vehicle's engines and corresponding control actuators. The control and information system reads the changes in attitude and translation from the sensor system, for example the IMU, processes the data and hands the control commands to the vehicle control actuator system for stabilization. In case of maneuvers and manual control, the guidance and navigation system hands the maneuver controls to the control information system, which will process it and hand it once again to the control actuators of the vehicle, and thereby perform the necessary velocity changes. Now we know how the navigation, guidance, and control worked in the Apollo missions. And that's how you get to the moon. Thanks for watching.